Hello, and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 4th, 2025. We're looking at an interesting ICLR conference paper titled, Standard Gaussian Process is All You Need for High-Dimensional Bayesian Optimization, published just over 3 months ago on January 22nd. This paper really questions the common wisdom that standard Bayesian optimization with standard Gaussian processes underperforms in high dimensions. The authors systematically investigate this belief through extensive experiments and theoretical analysis. Alright, building on that investigation, Figure 2 here gives us a visual confirmation of this gradient vanishing problem. It plots the relative change in length scales before and after training, and the gradient norm during training. You can see, especially in the gradient norm plots on the right, that the standard SE kernel with typical initialization has vanishingly small gradients. However, both the Matérn kernel and the SE kernel with the proposed robust initialization maintain much healthier gradients, allowing for proper training. Okay, so Figure 1 here really drives this point home quantitatively. It plots things like mean square error and gradient norm against increasing dimensions for different kernels and initial length scale strategies. You can clearly see in the bottom row the gradient norm plummets for standard initializations like 0.693 or 1.0, especially with the SE kernel. But look at the purple line. The proposed square root of deinitialization keeps the gradients healthy, allowing for learning. Alright, so this table provides more specific failure points. It shows the exact input dimension where gradient vanishing actually started to cause training failures for the Hartman-6 and Rosenbrock problems. You can see for the SE kernel, standard initializations like 0.693 fail around dimension 200. Matérn lasts longer. But look, the square root of deinitialization, no failure, marked by those check marks. This really confirms what we saw earlier in the plots. Okay, so Figure 4 really brings it all together, showing the final optimization performance on several real-world problems, ranging from 30 to over 1,000 dimensions. You can see standard BO with Matérn, the blue violins, consistently performs well, often competing with specialized high D methods. But standard SE, the solid red, frequently struggles. Crucially though, the dashed red violin, SE with robust initialization, performs strongly, matching or even beating Matérn and many others. This really shows the practical impact. Complementing those real-world results, Figure 3 here shows the optimization performance on several synthetic benchmarks, like Rosenbrock and Ackley, up to 300 dimensions. You see a similar pattern. Standard SE and solid red often struggles. But look at the Matérn kernel in blue, and especially the SE, with robust initialization in dashed red. They perform very competitively, reinforcing the effectiveness of these approaches, even on these challenging synthetic problems. Okay, and Figure 5 provides another look at performance on these synthetic benchmarks, focusing on runtime, specifically the maximum function value found over the optimization steps. Again, we see the standard SE kernel in solid red lagging behind, especially in higher dimensions. But both the Matérn kernel variants in blue and the SE kernel with robust initialization in dashed red perform really well, keeping pace with or even exceeding the specialized VBO method shown in green. So, wrapping things up, what we've seen throughout these results is that standard Bayesian optimization isn't necessarily limited to low dimensions like we often thought. The key takeaway is that the main bottleneck is often just gradient vanishing during training, especially for the SE kernel. But using Matérn, or that robust square root of deinitialization, really makes standard BO competitive again, even against specialized methods. Okay, that's it for this time. Thanks for watching. I'm Alex.